to this very short presentation on learning Query Sum product networks at AKBC. I'm Vaishak Belle, and this is joint work with Amelie Levray. To put this work in context, this rests at the intersection of two themes. On the one side, we are interested in learning probabilistic models, but as we know, these turn out to be intractable because inference itself is intractable. This has led to a kind of paradigm called as tractable learning, where the idea is that you learn a representation where you can compute conditional probabilities fairly efficiently. So the one we focus on are the so-called sum product networks. On the other hand, we're interested in dealing with missing data, which turns out to be a very interesting and important problem, specifically in the context of constructing knowledge bases. And here, often the conventional approach taken in the literature is to use imputation or completely ignore the problem. What we want to focus on here is a more principled approach to this problem with the use of imprecise probabilities via so-called Credal semantics. Just to bring people up to date, Credal semantics associates sets of probability measures with each of the random variables. Now let's consider why we would want to do this. Consider that in the absence of or in the presence of missing data, or in the absence of complete knowledge, if you try to learn single distributions, then you might get predictions that are unreliable and overconfident. There is then the added semantic value of knowing that the distribution of a random variable is not certain, so you can have an assessment of how confident you are about the prediction. Conversely, if you did have a pre-trained model where you know that there was missing data, you might consider some contamination strategies to have a more robust account of your prediction. Finally, there's been a very interesting use case positioned in the context of probabilistic knowledge bases, where you might have extracted tuples from large data sets like textual data and whatnot, and there you might consider that you would extract certain atoms, but those atoms you don't see, you typically consider improbable, right? So you might accord a probability of 0 to those atoms. Now, what would happen if you had a new source, as a result of which you would have to reconsider this atom as not being improbable? Certainly, if you'd need a more justified means of arriving at the posterior probability. And one of the arguments given in the literature is that maybe you should be according these unforeseen atoms to be given an interval between 0 and some epsilon value, which can then later be updated if you do observe this atom at a later stage. So these are some of the motivations for why Credal semantics are attractive in the presence of missing data. To see what these representations actually look like, consider that, again, sum product networks are representations where you can perform inference polynomial in the network side. So on the left-hand side, for instance, you see one such network. It's, as you can see, at the leaf node, you have these random variables, and these are essentially indicator variables, as it turns out, because they capture both the positive and the negative instances of these variables. And internally, you have sums and products, right? So this represents a kind of network polynomial for the underlying Bayesian network. And if you wanted to compute some kind of conditional probability or even a partition function, you can do this by a bottom-up pass. On the right-hand side, we see the Credal extension of this. And what you immediately note is that you no longer have numbers for weights, rather you have intervals. And these intervals are captured in this little figure we see. These are essentially sets of extreme points, capturing all possible values that these weights can take. What we're interested in is, in the presence of missing data, can we provide a justified means as well as an algorithm to kind of learn these representations efficiently and perform inference with them efficiently, so that we can have some kind of robust as well as a precise account of the confidence in our predictions. To kind of look at the evaluation of this representation that we learn, we contrast it and compare it to existing sum product networks. And mainly we're interested in two things. On the learning side, we want to see how good are the learned models, so what is the log likelihood? And on the inference side, we want to see how accurate are these models when you vary evidence as well as query atoms. And we're looking at two variants of Credal SPNs, one where we deal with the data set with 1% missing values, another where we're dealing with 5% of missing values. And of course, we don't expect you to see all the details on the left-hand side, but the bottom line is this. It turns out that we get really compact models, and almost in all cases, we get much better log likelihood scores. I'll point out that the paper includes a number of additional theoretical results, as well as complexity results, as well as an analysis of how inference can be done efficiently. Thank you very much for listening.